This is the first video for the practice-free response for Electrochem. This is the 1988 one talking about an electrochemical cell. So this is a voltaic cell, which means it's going to generate electricity. They tell you you have 1 molar of the tin electrode and a 1 molar of silver. All standard voltaic cells will be at the 1 molar. So then down below here, they do give you the reduction potentials and the voltage. So they say which one's going to happen at the electrode, which one's going to happen at the anode and the cathode. So when you're looking at standard reductions and it's a voltaic cell, the one that's the larger reduction potential is going to be reduced. So what you want to have here is the reduction takes place at the cathode. And in this case, the one that's going to be reduced is the silver plus 1 plus the electron, and it's going to become silver like solid. So you know that because it's more likely to be reduced. The other one then is going to be the anode. Sorry, it's being weird with the spacing, but it works. The anode is where oxidation occurs. And what you have to be careful with the anode one is they're written as reduction. So the anode one, you're always going to have to flip the reaction. So in this case, tin that's solid is going to have to become tin plus 2, and it's going to have to release 2 electrons for it. So that's how you know which one is going to do what. Then for part B, they want you to say, like, what's the overall reaction? So you're going to basically put these two together. Remember, with electrochemical redox reactions, the electrons have to match. So we have 1 electron and 2 electrons. So what happens is this first reaction you have to multiply by 2. So down here, what we get is we get tin, solid, but then up here the Ag plus 1 has to be multiplied by 2. So we have Ag plus 1, we get 2 electrons. On the right-hand side, we get 2 silver solids. We get tin plus 2 aqueous, and we get 2 electrons. Sorry, I forgot to put aqueous here. What you want to realize is the electrons are redundant, so then you can just get rid of them. So then you can either cross them off or just erase them, but then you end up with your balanced equation. That's the highest amount of like what you need to be able to do for redox. The next part they ask you to do is they ask you to calculate the standard voltage for this cell. So for this one, you just have to remember that the E naught is the E of the cathode minus the E of the anode. So for this one, you have to know the cathode, you have to know the anode. And what we do is just the E was the 0.80 for the cathode minus a negative 0.14. And we should get positive 0.94 volts. Couple of things you want to notice here. Even though we multiplied the silver by 2 to balance it, you do not do that to the standard voltage. It's an intrinsic property, so even if you need twice as much of something, the voltage doesn't change for that one for it. For the next one, they want you to calculate the equilibrium constant. So this one, your E equals 0.0592 divided by the number of electrons times the log of your K, and you're basically solving for your K value. So you calculated your E naught is 0.94. It's 0.0592. That's just a given constant. The electrons that were being transferred were 2. And then we have the multiplication of log K. So basically, you just have to simplify it as much as you can for it. So we have, oops, my calculator is missing. So basically, you just need to solve for your K backwards. I apologize, I don't have it solved out, and my calculator is out of batteries for that one. But this is a given to you on the chart. You just have to use it. For the last part of this one, they have you calculating a Q value. Basically, they did one very similar, but the tin concentration is still 1, but the silver is only 0.2, and basically what happens for what happens. So what you're doing is you're actually calculating a Q based on your reaction up here. So if you remember, Q is equilibrium base. It's the products over the reactants. it'll only be aqueous and gases. So if you look here at our one right up here, the silver solid won't show up. So on the top, we're going to have the concentration of the tin plus 2. And then on the bottom, we're going to have the silver concentration because the tin solid won't show up. So we'll have the concentration of the silver, and there's a 2 in front of it, so you have to square it. So what you want to understand is in a standard cell, on top you're going to have 1 molar divided by 1.00 molar squared. So in a normal situation, the Q is 1. In this situation, it's not though, so we need to see what's happening for it. So in this situation, the tin's staying at 1 molar, but the silver is staying at 0.02, and we need to square it. So what ends up happening is when you calculate this, you'll get a value. Your Q is greater than K. Q is greater than the normal situation, than a standard one, so your voltage will drop. And if you think about it, it makes sense. Tin is a product, and you have more of the product, and you have less of the reactant. So it makes sense that you wouldn't make as much of the product because you already have 1 molar of the tin plus 2, but you only have 0.02 molar of the silver for it. So you wouldn't actually solve out the problems, but that's just how you solve that one.